Hello everyone. Welcome to this Windpower Engineering and Development webinar on field verification of Wind Vortex Generators AEP, or Annual Energy Production, Increase with EDF Renewables, 3M Wind, and SmartBlade. I'm your host, Michelle Froese, Senior Editor of Windpower Engineering and Development magazine. Thank you so much for joining us. Just before we begin, I'll go over a few housekeeping items. At the bottom of your audience console, you'll see several application tools for your use that you can move to suit your preference. For example, you can click and expand the Q&A one, and this is where you can type your questions in during the webcast. I'd suggest not waiting until the end of the presentations, however. Type your questions in as they come to you, and we'll try to answer as many as possible before our time is up. If we run out of time or the question calls for a fuller response, it may be answered later by email. A copy of today's slide deck and additional materials are available in the resource folder, initially at the bottom of your screen. If you have difficulty, please click on the Help tab, the one with a question mark icon. Information there covers technical issues. And as not everyone who wanted to attend today's webinar could be here, you can help them learn from it by tweeting key points and the takeaways that you think are important. There is a place to tweet on your desktop, and just be sure to include the hashtag WindWebinar. An on-demand version of the webcast will also be available a day or two after the live presentation, and it can be accessed using the same audience link that was sent to you earlier. Now let me introduce you to our speakers. We have three presenters today. Joining us is Charles Kasmer, who manages the relationship between the EDF Renewables O&M services team and EDF Renewables asset managers. He has been in the wind industry since 2008 and spent 8 years with GE Renewables, where he held multiple different roles, most notably managing the operations of a 490 megawatt wind project. Charles holds a Bachelor of Applied Science in Energy Management from Bismarck State College. We also have Santosh Chandrabalan, who leads the 3M Wind business in his capacity as the Global Business Manager. Santosh's background is in composites, and he has spent a significant portion of his career in various leadership capacities in the composite, wind, and solar industries. His past experiences include research in process engineering, engineering management, global key account management, and he's an active member in many global wind and composite communities. Santosh holds a Bachelor of Science in Composite Material Engineering from Winona State University and a Master's of Science in Engineering Management from Southern Methodist University. Last but not least, we have Oliver Izela presenting today, Performance Engineer with SmartBlade, where he has worked since 2009. Oliver has a background in engineering physics with a focus on fluid dynamics and numerics. He's been involved in SmartBlade vortex generator development, as well as big data analysis and performance assessment. So with that, let us begin. Gentlemen, thanks for joining us. The microphone is now yours.
Thank you, Michelle, for that kind introduction. I would like to continue with the introduction of our Vortex Generator partnership. SmartBlade is our engineering expert on blade aerodynamics. They have designed the VGs to maximize energy capture by eliminating areas of stall across the blade. They do this utilizing their SmartViz methodology to analyze the flow of air over the blade during operation. 3M provides us with durable vortex generators with their patented adhesive tapes to ensure long life. EDF Renewables, we provide highly trained blade technicians to install VGs with an optimized installation procedure tailored per blade design. At EDF Renewables, safety is our first priority. We utilize SafeStart to instill a culture where safety is always our first thought. We currently have 10 gigawatts of renewable assets under contract, with all the major OEMs being represented in our fleet. We have a workforce of over 450 technicians to maintain our customers' assets and keep them running at peak performance. What is AEP? AEP is the annual energy production of our generators. A generator's output can vary based on a variety of factors, including low wind resources, high curtailments, or equipment condition. Blade leading edge erosion or uncalibrated pitch systems can lead to high losses over time. So how can we ensure that we maximize the turbine's AEP? Well, there's a variety of ways to do this. Pitch and yaw optimization, ensuring that the turbine's pitch and yaw alignments are properly calibrated to maximize wind capture. Our blade maintenance, blade inspections and repair, ensuring that you understand the condition of the blades to ensure they are free of defects that could lead to performance losses. Major component hardware upgrades. This is something a lot of people are doing right now with repowering their turbines with a higher rated drivetrain or power converter. And then we have blade aerodynamic optimizations, improving the aerodynamic properties of your wind turbine blades by adding, say, cord extensions, spoilers, trailing edge serrations, or vortex generators, which is what we'll be covering in this presentation. Now I'll hand it over to Santosh.
Charles, thank you very much for that introduction and bringing all the different parties together. So I want to take a few minutes to kind of give an overview about the vortex generator and what it is, how does it work, and what value does it bring before I turn it over to you on the installation and understanding more from the project here as well. But vortex generator, so VG is known as and referred to as VGs moving forward. It's an aerodynamic performance improvement device. So we know overall vortex generators has been in the overall industry for a very long time. It has been there to redirect the flow and delay any separation, so thus it reduces the aerodynamic stall. Vortex generators has been used even before wind space in the aerospace industry and have a very long history. But when it comes to the blade, it has been a lot of challenges. So we want to understand further on how our solution has resolved some of the major problems that you've seen in the industries with vortex generators. So with that, what the key idea behind the vortex generators is we have aerodynamic deficiencies at the root of a wind blade, if you may. So you are working with a structure that is actually a cylinder, which is not very aerodynamically efficient. So by addressing that deficiency and installing vortex generators at the right place with the right information, you would be able to generate a lot more AEP, as you explained, the annual energy production of a wind turbine. We as an industry in wind, we are always competing with other sources of power, and every ounce of energy that we can actually harness more from the wind turbines would be of great benefit to our customers and also for the industry. So from our experience, from our knowledge, we have now installed more than 2,000 turbines, and you can see on an average you can get up to 2.5% to 3% increase in power by installing vortex generators at the key and the right locations, if you may. Now, with that said, one of the key challenges that I was mentioning to you when we were getting into vortex generators, one of the key challenges in the industry is you are trying to attach a plastic or a metal or any kind of vortex generator to a big, large composite part which continuously has flex. So we are trying to bond dissimilar materials that goes through very severe weathering conditions and has a very long life cycle. So what happens is in that case, you need a solution that is going to be bonding really well. Plus, from an aerodynamic standpoint, once you correct the aerodynamic efficiency, certainly you will increase the power output, but we want this vortex generator to stay on the blade for a significant amount of time so that you are from not only making it a break-even solution, you also enhance the profit coming out of the increased power generated by a vortex generator. So the problem here that we're trying to address is we want a solution that can help to bond, but we also want a solution not only will bond well, it has to last for multiple years so that you don't have to go back and fix and repair any of these vortex generators. Traditionally, the industry has been bonding with different kinds of adhesive, and we as 3M have a lot of different experience in bonding and adhesive here. So one of the challenges that we understood from bonding vortex generator to adhesives are we have a flexible blade that moves significantly, and you have a thermoplastic or metal, any kind of surface that you're trying to bond that will expand at different rates, right? So your coefficient of thermal expansion will be very different. So as the turbines are operating for a very long time with the CTEs in play, plus also all the weathering in terms of heat, humid, icing, all those different conditions, you not only want an adhesive solution that bonds and being strong, it should also be forgivable. So it needs to be flexible enough such that with these variation, it'll still continue to bond and have an extended life. So that's when we move to our acrylic foam tape solution to make this vortex generator last much longer in the field, even given this very difficult conditions. So with the acrylic foam tape, what we're able to do is bond a vortex generator, and that has the flexibility. So during tough conditions, it is actually tough and strong, but at the same time, it is flexible, so it does not give up. So the flexibility transfers all the power into it. So that's the first problem we are trying to solve. So we need to have a solution that has to be installed correctly to address the stall so that you can increase and optimize the increase that you can get from vortex generator. And then you also need to have a solution that will be staying there for a significant longer amount of period. So once you have actually know how to bond the solution, in the field, it is really important to understand how and where to install the vortex generators. That's one of the key aspects. Many times, vortex generators are designed from a blade design compared in a computer CAD model, if you may. And yes, it can be very accurate from a modeling standpoint, but is it realistic from a blade that is in the field that has been operating? And as we know, blade manufacturing from a CAD design to a final model, final part, there's a lot of variations that can happen. So partnering with SmartBlade and EDF, there's a new technology that we were able to develop called Smart Visualization. Smart Visualization enables to visualize the blade and the airflow around the blade at the root area to understand and capture the key deficiencies that are happening. It helps us actually to look at the airflow and understand when we can actually and where needs to be the vortex generators are installed. So with the help of multiple different cameras and very high-end data analysis, we can actually look at the flow, understand where the separations are. Once we understand where the separations are, then we can actually go ahead and install the vortex generator at the right places to make sure that it's increasing the efficiency overall of the blade and not affecting any performance in there. So that is a key differentiator in the solution, because rather than moving forward with a solution that is based out of a computer CAD model, the differentiation is in real time. We understand the airflow, we understand the deficiencies of the blade, and we understand how to resolve it by installing the vortex generator at the right location for each blade type, if you may. So it's almost a tailor-fit solution for every model of turbine and blade that you have. So that's actually a very good visual proof of that here. So you can see here, what you can see here is a picture where we have done the flow visualization. You can see the blade is in operation, and we go ahead and install very many flow tufts on the root end of the blade, as you can see at various different locations. And we run the turbine for a certain amount of period to understand how the airflow is. As you can see, this turbine is in operation. So in the leading edge, you can understand and see where all the flow tufts are perpendicular to the blade length, showing that the wind has attached to the surface and it has actually flowing through the leading edge, causing the flow tufts to be perpendicular to the blade direction or parallel to the wind direction. But you can see something happening after the first few flow tufts. You can see now, as we move forward into the chord of the blade, the flow tufts are now parallel to the blade direction or blade length and perpendicular to the wind direction, which is odd, right? So essentially what we're seeing is we see that the wind is coming and attacking the leading edge. The flow continues to flow on the leading edge, but at a certain point you see flow separation. So essentially that surface energy is not being used and we actually have a deficiency. So by looking at this and getting the feedback real time with the help of multiple cameras and taking and inputting those feedback into a very detailed analytical system, we can understand where that stall is or where the flow separation is, which will help us to install the vortex generator efficiently at the right location. So now let's say we have a good understanding of the flow is and where the separation happens. Now we can go install the vortex generator. So what next? Actually, you can see in the next picture, we can understand what is the impact of these vortex generators when installed in the right way. So there's the visual proof. Certainly we can see the increase in power later in the presentation on how this actually increases the output of your wind turbine. But here is a quick visual proof. The same turbine that we saw on the left-hand side, the same blade, now you can see on the right-hand side after the vortex generator installed with the data that is obtained from the flow visualization. Now you can see a major difference. Almost most of the flow tufts now are in perpendicular direction to the blade length, essentially forming the flow is being attached to your blade, so it is actually parallel to your flow direction in here. It's a huge difference between the left-hand side picture and the right-hand side picture. What does the vortex generator do is demonstrated really well in this two pictures where it shows the vortex generators has re-energized the flow where it is being installed, and it has actually optimized the flow to ensure that you have the maximum output or taking into consideration of the maximum aerodynamic efficiency that you can get from the root side. So that's the key solution that we have when we're looking at the combination of SmartBlade's smart visualization combined with a material that will help you last significant amount of time in installation. You have a solution that not only is robust, but it is also very precise to get the optimum out of your vortex generator installation. So with that said, I will pass it on back to you, Charles, for the rest of the presentation here.
Santosh, thank you very much. Last year, we worked with one of our customers to identify a site where we could perform a pilot to verify the AEP increase of the vortex generators. With our customer, we looked at their fleet and determined that they had a high population of GE turbines within their fleet. After looking at their individual sites, we found Bobcat, which was a very low turbulent site, very flat terrain. They had a consistent prevailing wind out of the southeast, and they also had a lot of turbines on the southeast side of the park that had no turbines in front causing low turbulence, low wake. The site also has access to a historian with 1-second data, so we knew we would have very reliable data to analyze, and that brings down the uncertainty factor when we do our analysis. So last summer, we performed the installation at the Bobcat Wind Farm on 6 turbines. As we've said before, each installation is blade specific. So utilizing the SMARTviz, every blade is mapped and modeled so that they all have the ideal VG line to maximize the AEP increase. Off of that SMARTviz, we tailor a blade-specific installation manual, and we have blade-dependent installation templates that we use to ensure that we have a precise, robust, repeatable installation every time. We have very minimal downtime. We look at about 8 to 10 hours of downtime one day to perform an installation on a turbine. We currently have the ability to install VGs on 20-plus turbine models. And this can grow if a customer wants to model a turbine that we have not modeled. We can do a SMARTviz and very quickly determine what the VG line is and go out and perform installations on that turbine. Now I'll pass it over to Oliver to take us through the results from Bobcat.
Thanks a lot, Charles. Before we go on with a detailed look at the Bobcat data, I would like to introduce you to our general trial process. Turbine trials are a relatively important part of the whole process since they allow us to evaluate the value of our vortex generator solution in form of AEP numbers that we can expect in real life. Therefore we have established a well-defined trial process that allows us to gain results with highest certainty. Looking at this, it consists basically of 4 steps. The first phase is always the experimental design. Here we do a major review of historical wind farm data in order to find proper trial candidates. And we are looking for turbines that have clean inflow conditions. We do major revision on the operational history of the turbine, and we also check for good data availability. At the end of this process, we should come out with at least 6 to 10 turbines in order to have a proper sample size also for the trial. When the turbines are selected, we can go on directly with the vortex generator installation, which is a pretty efficient process based on rope access, and as Charles already mentioned, takes approximately 1/2 to 1 day per turbine. After the installation, there's nothing else to do than waiting for data being collected. The duration of this data collection period depends a little bit on the wind speed conditions during the data collection phase. But in a vast amount of trials, a rule of thumb of approximately 3 months of data collection has established. When data is collected, we can go on with the final step, which is the data analysis, the review of the collected data set, and the final assessment of the performance of our vortex generators. On this slide, I would like to give a brief retrospective on the effect that we are evaluating. Here we can see the results of a flow visualization based on our SMARTviz technique. On the top of the image here, you can see the flow visualization of a blade with no vortex generators installed. And as you can see here, the red large area is aerodynamic stall, which we detected. And the stall extends up to approximately 30% of the blade span. After installation of vortex generators, you can see the same flow visualization on the blade here below. And as you can see, there is no stall anymore. So we have completely eliminated the stall area with our vortex generators. This is a significant improvement of the blade aerodynamics, and the purpose of the whole turbine trials now is to evaluate how much AEP gain we can expect from this aerodynamic improvement. For our trials, we use a relatively straightforward method, which we used in a vast amount of trials before, and which has established quite robust results for us. Here we use always a test turbine and a control turbine, whereas the control turbine is a turbine that is running as a reference and remains unmodified throughout the entire trial period. The test turbine is a turbine that we selected and paired with the control turbine, and the test turbine will have reduced installed after a certain period. In order to account for initial differences in the AEP of both turbines, we do a power output comparison for the historical period, where both turbines are completely unmodified. The same power output comparison we do for the post-install period, where we now have the test turbine with vortex generators installed. The overall difference between the historical period and the post-period will give us the final AEP gain that we achieved through the installation of vortex generators. This method we used in a vast amount of trials, and we had also successfully reviewed by DNVGL, and the method was also successfully validated against rather scientific methods such as the TAMI method, which is multidimensional power curve method. In this slide, we will see briefly how the power output comparison between test and control turbine is done. Here we compute for each data point the power output difference between both turbines, and we sort this data into discrete bin buckets that we create based on the control turbine power. In the final step, we compute all the bin-wise statistics for each power bin, and we are able to resolve this way the power boost of our vortex generators for the entire operational regime of the wind turbines. The actual Bobcat trial, here we see the results of our experimental design phase. As Charles already mentioned, the conditions at Bobcat are pretty uncomplex. So we deal here with flat terrain, a low vegetation, and we don't have any much obstacles in the prevailing wind vectors. The Bobcat wind farm is a relatively low wind speed site with an annual mean wind speed of 6.6 meters per second, and we have a pretty pronounced prevailing wind sector in the south-southeast direction. Therefore, we identified quite a lot of test turbines in the southern rim of the wind farm because we can expect clean inflow conditions from these wind directions here. As you can see in the wind farm layout here, we have 6 vortex generator turbines, so 6 test turbines installed with vortex generators in blue, and we have also for each vortex generator turbine at least one control turbine, which is colored here in orange. For the complete trial, we had a 12-month historical data period available, and we collected 6 months of data post-installation. Looking at during the Bobcat trial, we can see that we have quite similar distributions for the historical period and the post-install period. As you can see here in the wind distribution for the historical period, we have captured quite some more high wind speed data, and in the post-install period, we have captured more low wind speed data. In order to align both distributions, we can use as well distribution sampling. Here we define the post-install wind speed distribution as a target distribution, and we sample the historical data set such that we meet this target distribution. This way we can ensure that all wind speeds are covered for both periods in the same way. One of the most important steps before really going to the power output comparison between both turbines is a proper dataset cleaning. The main objective of the dataset cleaning is to assure that both turbines, test turbine and control turbine, are running in normal operational states. Therefore, we remove start-stop scenarios, fault events, and also third-party curtailment events. Another objective of the dataset cleaning is to remove inconsistent and corrupted parts of the data set. For example, as you see on the bottom image here, in a power time series plot, we might deal with large data gaps that are filled with artificial interpolated values, and these values do not contribute well to the whole analysis. On the top graph here, you can see the result of the proper dataset cleaning. You can see in red colored in red all the data points that are off normal operation and that are corrupted. And you can see in blue the clean data set here. And as you can see, the clean data set is a pretty well-shaped power curve, scatter plot. One thing that we observed when we had a look at the Bobcat data was that we had some problems with the opposition signal here. When we look at the bottom left graph here, we see a comparison of yaw positions between test turbine and the control turbine. On the x-axis, you see the yaw position of the control turbine, and on the y-axis, you see the yaw position of the test turbine. What you should see, if everything is fine, you should see only one band here in the middle of the graph, but obviously in this case here we see also secondary bands, which shows us that the data shows that both turbines are not really aligned in terms of yaw position. Since both turbines are neighboring turbines, this behavior is not expected, so that we had to deal with corrupted yaw position calibrations here. In order to tackle this problem, we used some nearby MetMass data and compared the yaw positions of our turbines with the MetMass data. Looking at the statistics on the top of the graph here, you can see in blue the turbine E72. So you see the difference of the yaw position to the MetMass data, and you can see the blue curve here is close to 0 all the time. This means that turbine E72 is well aligned and that the yaw position signal is correct for this turbine. For the turbine E71 instead, you see that in July to October, you have a difference to the MetMass wind direction of -100 degrees, and in another period, in the later period, you see that this difference is only -30%. In order to correct this miscalibration, we applied these correction factors that we gained through the MetMass wind direction to the yaw position signals, so that we get the corrected yaw position. On the bottom right of the slide, you can see the graph, the same graph that we saw before with the corrected yaw position signals. And as you see now, there's only one band in the middle of the graph, which shows that both turbines are well aligned now. Another issue that we observed during the review of the entire trial data set was that we have some further modifications on some turbines done. This violates a bit the fundamental requirement of the overall method, which says that the only modification of the test turbine, in this case, should be the installation of vortex generators. In order to see what's going on here, let's have a look at the left graph on the slide. Here we see the active power versus the generator speed for a sample turbine. And you can see the linear region here, which is the variable speed regime, and you see two discrete bands, which are to distinguish maximum RPM regimes. These different bands are caused by the wind boost package that are installed on the GE platform in Bobcat. And whenever wind boost is switched off, you have the lower maximum RPM, and whenever wind boost is switched on, you have a higher maximum RPM that is set. Another problem that we see here on this graph is that if we zoom in into the speed up curve, we observe that we have two different bands in the speed up curve. After further investigation of the data set, we could connect this different speed up behavior directly to a pitch adjustment on some turbines. Since we see that this pitch adjustment causes a significant impact on the speed up curve of the rotor, we can also expect that it has a significant impact on the power output of a turbine. If we wouldn't clean up the data set, we wouldn't be able anymore to distinguish the effect of our vortex generators from the effect that this pitch adjustment might have on the active power output of a turbine. Therefore, we had to remove quite some couple of test pairs that we initially wanted to investigate. The rest of the remaining pairs show the behavior, as you can see on the right graph here. We don't have any adjustments done, so we have a unique speed-up curve of the rotor, but we still have two different controller modes where we have the wind boost off and wind boost on bands here. Another thing that we observe is that for the lower power regime, below 500 kilowatts, there's no real difference between having wind boost on and off. Since the major part of our data in the post-install period was collected during seasons where wind boost was activated, we also had to reduce the historical period to the data set where we also had wind boost activated in order to compare to the right reference. Having done the complete data set cleaning, the next step we did is proper wind factoring. The main objective of the wind factoring is to assure that both turbines, the test turbine and the control turbine, see similar inflow conditions so that we are able to make a fair power output comparison. Therefore, we had to exclude waves, obstacles, and everything which disturbs our prevailing wind vector. Looking at the graph on the left here, you can see the wind speed ratio, which is the nacelle animator wind speed of the test turbine divided by the nacelle animator wind speed of the control turbine. This wind speed ratio is binned according to discrete wind direction bin buckets, whereas we use the yaw position of the control turbine here. And for each bin, we show here in form of box plots the statistics. And as you can see here in the eastern and western wind sectors, we have heavy wake conditions. So the wind speed ratio is far away from unity, and we have also a large data spread here. Looking at our prevailing wind, we have pretty clean conditions here. We have a wind speed ratio of unity and a relatively low spread, and we don't see any wind direction dependence. So these are optimal conditions for a fair power output comparison. After the dataset cleaning and also after the proper choice of a clean inflow factor, we can do the power output comparison for the historical and the post install period and do the general comparison between both periods. On this slide here, you can see the resulting graph. You can see on the x-axis of this graph the active power bin bucket of the control turbines, and you can see on the y-axis the power increase that is caused by our vortex generator installation. Looking at the power boost across the different operational regimes, we observe that for the low power regime below 800 kilowatts, there's no significant impact on the power output of the turbines from our vortex generators. This regime corresponds well with the variable speed regime of the turbines. As soon as the variable speed regime is left, we see a significant power boost starting at like 800 kilowatts and reaching a maximum peak of approximately 80 kilowatts at approximately 1,400 kilowatts of the turbine. When we reach a rated region of the wind turbine operation, we can see that this effect disappears and goes to zero, which is an expected behavior since the pitch controller is limiting our power output of the turbines. What we also see on this graph here is that we, on the remaining parts, that we have a relatively good correlation between the results. Now that we have detected the improvement in power output of the turbines, there's one final step that we have to do in order to compute the AEP on our turbines. In order to transfer this power output to AEP gain, we just need to apply our power distribution at the site. At this graph here, you can see in the background in bars the power distribution at the Bobcat wind farm. And combining this power distribution with the power increase that we measured, we can get the AEP increase at this specific case. With the same method, we can also use power distributions from other sites that are derived by wind speed distributions or also derived directly by looking at historical power data of a wind farm, and we can transfer as well the results from Bobcat to other wind farms. If we do the final step, we can see the AEP increase for each individual test pair at Bobcat. For the first pair, we can see a 1.4% AEP increase, and for the second pair, we see a 1.8% increase. As an overall average for the Bobcat case, we can see a significant AEP increase of 1.6%. The uncertainty of this case was computed based on a bootstrapping method, and we can state that the 95% confidence levels span an uncertainty range of 0.1%. The significant AEP increase of 1.6% fits pretty well into the results that we gained through a vast amount of other trials. Now I hand it over to Charles in order to get a conclusion for this webinar.
Oliver, thank you very much for presenting on the VG trial results from Bobcat Bluff. I also would like to thank Santosh for participating today and providing a great overview of the VG product itself. If anybody would like to learn more about our VG offering, please feel free to visit us at AWEA next week. We have booth 1634 in the West Hall. Thank you very much.
Great, informative presentation, gentlemen. Thank you so much. Now, let's take some questions from the audience. First up, what is the variability that an owner could expect if they installed Vortex generators on a different site with the same turbine model?
The general range that we see when we have a look at the Bobcat trail results is in the range of 1.5 to 2%. Although we have to mention that the Bobcat is on the lower end of the range because here we deal with a low wind speed site. For sites that have a higher wind speed, annual mean wind speed, we would expect something like 1.8 to 1.9%. And we can also use the Bobcat results to directly compute also the expected gains at a specific site if we get the wind speed distribution.
Makes sense. Thank you. How would a complex site with many elevation changes affect a pilot?
Pilots at really complex sites are feasible, and we have done so far quite some trials also on sites where we have a lot of hills and mountains and a lot of different flow effects. What we observed is that these trials are also feasible, but that we see, of course, a higher uncertainty in this case. So if we deal with the trials that have complex soil, we should check for a larger sample size in order to have still a robust result with although the uncertainty is slightly increased.
Sure. Another question for you. What happens if some or all of the Vortex generators happen to fall off of a turbine blade? We have quite so far installed a couple of thousands of turbines for quite some long period, and did not really happen till now. If some Vortex generator would fall off, we would expect a minor change in the performance. So as long as this is a low amount of Vortex generators that fall off. In worst case, it's a completely theoretical case, but worst case, if they would all fall off, then we would just go back to the original unboosted power behavior of the turbines. Thanks, Oliver.
And
go ahead.
Oh, this is Charles. Another thing I'd like to add to that is to ensure that you continue to maximize the production of your turbines. The ideal methodology would be to, every few years, via blade inspections, when you get to that tipping point where you start to lose enough VGs to lower the AEP boost, you would go back and perform maintenance by reinstalling VGs where the VGs have fallen off.
Thanks, Charles. Do VGs create additional noise at all at a wind site?
From theory, there's no noise increase expected. Actually, what VGs do is they eliminate aerodynamic stall, and actually aerodynamic stall is a very significant noise source, and if you put VGs on it, you would remove that noise source. Although this is like, we have to always keep in mind that we here speak about the root region of a wind turbine blade, and actually noise gets only problematic in the tip region. So what we could say here is that VGs reduce slightly the noise, but this reduction wouldn't be really noticeable because it's on the root region. So the tip is much louder than the root region.
What about turbine loads? Do vortex generators increase the load at all?
Also here we have to consider that we are just modifying the root region of the wind turbine blades, so therefore we do not expect any critical modification of the turbine loads. And we did also quite some investigations, so we had some computations of full load case sets, also in collaboration with the manufacturers, and all these analysis resulted in the statement that there's no critical modification of any turbine loads. So the upgrade with water generators in the root region is completely uncritical considering loads.
Fair enough. What about the tip of the blade? I have a question here. If vortex generators make sense on the tip of the blade?
In theory, we should see at the tip of the blades pretty clean airflow, and we wouldn't really expect any separation at the tip region. So in real theory, there shouldn't be necessary. However, based on our SMARTviz technique, so we do kind of a flow analysis of our blades, we can see that sometimes there is actually stall in the tip regions. The reason for that might be production issues or leading edge erosions or other disturbing parameters on the blade. And if you detect the stall also at the tip region, then it makes sense also to go for VGs at the tip in order to eliminate this stall.
Fair enough. One last question for you today. If a blade already has OEM installed VGs, does it make sense to add on these vortex generators that you've been discussing as well?
Yeah, we have seen also like OEM VGs at the field, and it might make sense in some cases to also replace them. First of all, what we see is that the design philosophy is slightly different. We have this SMARTviz technology where we can see directly the aerodynamic behavior of a blade directly on the field. And when we use this technique, we see also potential for some blades where we already have OEM VGs, that there's a chance to again improve the performance by modifying these VG lines in order to put extra VGs in some places.
Excellent. Thank you so much. We are at the end of our allotted time for today, ladies and gentlemen. Once again, this webcast will be available for reviewing at windpowerengineering.com. One final message: you can follow Windpower Engineering on Facebook, Twitter, and LinkedIn. I'd like to thank Charles, Santosh, and Oliver for their insightful presentations, and everyone else for their attention. From staff here at Windpower Engineering and Development, we wish you all a good and productive day. Thank you.